vamos a tener la presentación disponible en inglés o en español. Entonces, ahorita vamos a activar la opción de interpretación y ustedes van a ver en su pantalla en la parte de abajo la opción de escoger si escuchar directamente a Paige, que va a presentar hoy el tema, o pueden escucharlo en español. Yo voy a hacer la interpretación. Entonces,
Good. Okay. All right. Hello, everybody. Welcome to the Landscape Metrics in R workshop. My name is Paige. I am a PhD student in the Silvis lab, and I study fire and birds. And I use a lot of methods from landscape ecology in a lot of my research, including some of the metrics that I am going to be presenting for you all today. Okay. So to get started, I'm quickly going to touch on landscape ecology, which focuses on spatial patterns across the landscape and the ecological processes that are influenced by those patterns. Landscape ecology methods are often used to study disturbances, landscape change over time, connectivity, fragmentation, and more. And many of the methods that are used in landscape ecology aim to quantify landscape structure. So the metrics that we'll be going over today are one method to do so, but there are other approaches that can be used, like morphological spatial pattern analysis, circuit theory, network analysis, and many more that can be useful if landscape metrics don't suit your needs. So landscape metrics are quantitative measures that are used to assess and analyze the structure and composition of landscapes. There are a lot of reasons why ecologists or managers might want to quantify patterns across a landscape. You might want to see how a landscape has changed over time, compare the structure of one landscape to another, determine how organisms move across the landscape, or track effects of a disturbance on an area of interest. There are hundreds of landscape metrics that have been developed to address ecological and management questions. Many of them are redundant, and the best metrics that you might want to use will depend a lot on the questions that you are asking. There are quite a few different softwares and packages that are available for calculating landscape metrics. FragStats is a software that was first developed in the 1990s that helps people calculate landscape metrics without needing to do all of the calculations by hand. It's extremely widely used, and many of the newer softwares, tools, and packages that are used in landscape metrics are based on FragStats, including the one that we're going to be using today. Both ArcGIS and QGIS, if you use those softwares often, are also used for landscape metrics. QGIS has a plugin that's called Landscape and Ecology Statistics that is based on FragStats, and there are multiple ArcGIS toolboxes that have been developed to calculate metrics as well. Today, what we're going to be using is the R package called Landscape Metrics. It is based on FragStats completely, and it's free, simple, accessible, and open source. The links document that I shared with you guys in the workshop materials has links to both the CRAN package and the GitHub for this package. All the other links also should be included on that links document. And the documentation for the package is also available in the PDF in the folder as well. I am just going to go ahead and jump right into using that package. So if you plan on following along with the tutorial today, go ahead and open up the R script that is included in the workshop's materials folder. You're also welcome to do this tutorial on your own time. The R code has a lot of documentation, and we're going to see about sharing this PowerPoint after we're done today as well. Depending on your computer, some of the sections of the code might take a little bit longer to run. So if a particular function is taking quite a while, then you're welcome to skip it or just do it later in your own time. All right, so we're just going to go ahead and get right started. So to get started, we're going to want to install and load all the packages that we're going to be needing for this tutorial. That's this chunk of code here. In the provided code, I have tidyverse, landscape metrics, Terra, and SF. The first three are required to use for the package, although you won't really need to deeply understand how to use tidyverse or Terra in order to use landscape metrics. They're just sort of built into the code itself. SF is a package that's mostly used for vector data, and it's not usually required for landscape metrics. However, today we're going to be working with shapefiles just a little bit, so I do have it installed. So once those are all installed and downloaded, we're going to go ahead and load in and visualize the data to get an idea for what we're working with. To load these files from the folder that I sent you guys, go ahead and navigate to them in your file manager. They're located in the Lenine shapefile and land cover raster folders, respectively. Once you are able to find those in the landscape manager, go ahead and copy the path and then paste it into the stread function here, and then the two rast functions as well. You're looking for the Lenine shapefile.shp for stread. And then you're looking for the Lenine land cover raster for this first rast function, and the Dane land cover TIFF file for the second rast function. One thing that R is really particular about is the direction that your slashes are facing. You can see them here. So make sure that all of the slashes are forward slashes and not backslashes in your file path, or else R might not be able to read the file in and it won't run properly. So once that's taken care of, we're just going to go ahead and run the two plot functions so we can take a look at the landscape. So the first layer is this colorful rectangular layer that's of our raster that is around the area of Lenine National Park in Argentina. The red line is the shapefile that shows the actual boundaries of the park. The landscape metrics package requires a raster of land cover or habitat types to calculate any of its metrics. And the one that we're going to be using is the European Space Agency's World Cover Layer, which has a 10-meter resolution and is available globally. When we plot the land cover raster, we'll see that the extent goes past the park boundaries here. And the landscape metrics package requires a raster that is set to your exact boundaries of your study area. So we're now going to run a line of code here. This is the mask function from Terra to go ahead and crop the raster so that we can only see the pixels within the park included. When you plot the cropped raster, you'll see that the raster now directly follows the park boundaries. So we have it here. And for this workshop, we are going to be focusing on Lenine National Park, but we also will want to load in a raster of Dane County, Wisconsin, which is where our lab is located. Some of these metrics will be better explained with multiple landscapes in them to compare. And when comparing landscapes, it is important that you use the same type of raster data to avoid any bias. So since the ESA world cover data is a global data set, we're able to use it for both locations easily. And if you haven't already, you can go ahead and run the plot function to take a look at the Dane County raster. This one is already cropped to the right extent, so we can just move right ahead with it. So now we're going to go ahead and get started with some of the functions that are available in the landscape metrics package. This first function is called check landscape. You should be able to run this function every time that you load in new raster data to make sure that it is compatible with the landscape metrics package. So we're going to run it both for Lenine National Park on the top and then Dane County on the bottom. And then this is the output that you'll see for that function. So it shows you what it was checking for. This function wants to make sure that you have a coordinate reference system that is projected. So that's this part here. Both of our rasters use Universal Transverse Mercator, or UTM, which is a projected coordinate system. So we're good to go with both of them. It is also checking to make sure that the raster is in meters as the units, which we can see here, they both are. The class column shows that we have an integer data format, which means that every pixel on the raster has an integer value. and those integers correspond with a certain land cover type. The last thing that it's going to be checking for is that we have a reasonable amount of land cover classes or habitats. That's this column here. I'm not really sure what the upper limit that they consider reasonable is because it doesn't say in the documentation, but the function will tell you if it is unreasonable. So the Lenine raster has 9 classes and the Dane raster has 7, and the function has determined that both of those are reasonable. So we get a check mark in the OK column because everything is checking out. If any of these requirements were not met, we would get an X in the OK column, and the function output would include a warning telling you where you went wrong. So you can correct it. But now that we've gotten the OK, we can go ahead and take a look at some actual metrics. So from here on out, the functions could take a little while to run depending on how much memory your computer has available. And if a function is taking too long and you don't want to wait for it, you are welcome to skip that step. I will have screenshots of all of the outputs on every slide, and you're welcome to run the code after the workshop as well. So now we're going to start by running the list LSM function to see a list of all of the metrics that are available in the package. If you want to see every single available metric, then you can just leave this function blank like this, and it will generate a full table. When you do generate that table, the output table will show the metric, which is this column here, and that's the abbreviated name that's used by the package, the name here, and that is the full unabbreviated name of that metric, the type, which is the metric's category, and it's organized by the type of ecological pattern that the metric describes, and that's designated by FragStats initially. The level here, which is the spatial scale that the metric is calculated to, and then the function name, which shows how you will call the landscape metric in R. Before we run any other code, we're going to take a pause, and I'm going to quickly explain the different levels of scale that the landscape metrics package has and the different types of metrics. So there are 3 available spatial scales. Starting with the finest spatial scale, we have patches. And these are a very important concept in landscape ecology, and they're often used as a unit of measurement in metrics, even if you're measuring things to the class or landscape level. A patch is an area of continuous land cover or habitat. And in this figure, there are many patches of both the blue and the green class. When you calculate a metric on the patch level, you're going to return a value for every single patch that's present on the landscape. For example, if we calculated area at the patch level, the package would output the number of pixels in every patch. And this takes a lot of computational power and would not be very useful on landscapes that are as large as what we're looking at today because we have thousands of patches. That being said, the metrics we will look at use patches as a unit of measurement frequently, so it's important to understand how they work. One important thing to note is that the exact number of patches that's present on a given landscape is dependent on how you want to determine how 2 pixels are connected. The first option is to use the 4-neighbor rule. So this would be to be in the same patch, 2 pixels must share the same edge. So like here or this. And if we use this rule, that means that there are 10 separate green patches across the landscape. The other option is to use the 8-neighbor rule. And under this rule, pixels can share an edge or they can share a corner like these. So the 8 pixels surrounding the center could all be in the same patch. We see that using this rule, there are only 5 patches on the landscape, and this shows that the way that you count patches can make a really big difference in the values that you get for your metrics. The next level we have is the class level. Classes are different land cover types that are defined by the land cover raster that you're using. In this example, we have 2 classes, green and blue. The ESA world cover dataset has 11 classes total, When we crop the rasters to our locations of interest, we see 9 of those classes are found in Lenny National Park and 7 are found in Dane County. When you calculate metrics on the class level, all of the pixels, or in some cases, all of the patches of the given class or habitat type are included in the metric calculation. And the output will be reported on a per class basis. For example, if we calculated total area on the class level, the package would report the number of pixels of each land cover type that are present. And we will look at metrics calculated at this level quite a few times today. The last level that we have is the landscape level. So this is your entire area of study, and it's made up of many patches and classes. Landscapes can be any size or shape, and when you calculate a metric at the landscape level, it will report the number of pixels in the map regardless of the class or patch that they belong to. Oftentimes, landscape metrics calculated at the landscape level are looking at patterns of where patches and classes are located in relation to one another, and it generates a value that's able to summarize that pattern. Diversity and aggregation metrics are often measured at this level. So now that we have levels explained, I'm going to quickly describe the different types or categories of metrics that are available in the landscape metrics package. These come from FragStats documentation and are used to organize the metrics by type of ecological pattern that they describe. I don't have time to get into too much detail about every single type, but I do suggest checking out the R package documentation and the FragStats documentation if you would like to learn more. The package documentation is available in the supplemental workshop materials, and the FragStats web page is also linked in the links document. First, we're going to look at area and edge metrics here. These describe size and edge characteristics, typically averaged or totaled across a class or a landscape as a whole. Some examples would be area per class, edge density or edge per area, and the largest patch index. Next, we have shape metrics. These are often calculated at the patch or class level and describe the shape or the complexity of patches. These could be useful for edge effects, patch complexity, or compactness. And some examples are shape index or compactness and the perimeter to area ratio. Then there are the diversity metrics, and they assess variety and evenness of the land cover classes across the landscape. These metrics include things like the Shannon's diversity and evenness indices. Next, we have core area metrics. These look at the area away from the edge or the core area of habitats. They're helpful for assessing the interior of habitats for sensitive species and can be measured at the patch, class, or landscape level. Some examples are total core area or disjunct core area. And our last option is aggregation metrics. And these are measured at the class or landscape level and show how clustered or dispersed patches of the habitat are. They're useful for connectivity and fragmentation analysis, and some examples include contagion index, mean proximity, or mean Euclidean nearest neighbor distance. So now that we've gone over all of our levels and types, we can get back into the actual coding. So let's go back to this list LSM function and find more relevant landscape metrics. If you know generally what type and class of metric that you want, you can also use this function to filter by those things. And in this example, we filtered it by level, so it will only return options that calculate metrics to the class level. And we also filtered it by type, so it will only return shape metrics. You're also able to filter by metric or by name, but there are less use cases for that. So these are the important ones. When we run this line of code here, this will be our output, and it will return a much shorter list of available metrics that fit what we're looking for. This function is pretty useful if you know approximately what you're looking for, but want to see the options available so that you can pick a metric that's best suited for your needs. If you run the list LSM function and find something that you think would be interesting, you can add and run a line of code that's formatted like question mark, name of the function, and then empty brackets. This will pop up a help page at the bottom right-hand corner of your screen that shows the documentation for that function. Here's an example. Here I took the function that list LSM returned and decided to read further about it. It shows all of the potential arguments for the metric, what it's describing, and the math behind the metric here. This is a really useful tool, and you should feel free to use it at any point during the tutorial if you would like to learn more about the functions that we're using. So now that we've gone over getting the data ready and a couple of general functions, we can get into calculating some landscape metrics that are available in the package. I will go over an example or two of each of the types of metrics that we talked about. First, we're going to start with some area and edge metrics since they're relatively easy to describe. For each metrics, I'll show the input line of code here, and then the output. And I am also including an equation for some of the metrics to show how R is calculating things on the back end if you're interested. And the first one that we're going to be doing is proportion of the landscape that falls into each class. So this is called LSM C-P land. And you can go ahead and run it on the Linero raster. This is a class level metric that shows which classes are most common in the landscape. The output value is a percentage, so it adds up to 100. In Linero National Park, we can see that class 10 or tree cover, I have the classes down here, is most common at 56% of the landscape. And then that's followed by class 30 or grassland, which is 22% of the landscape. And then finally, class 60 or bare or sparse vegetation at 12.5% of the landscape. The second metric in this category is going to be edge density or edge per area. And we're also going to calculate this on an edge level or on a class level. Edge density is the sum of all edges of the same class divided by the total landscape area in hectares. So how many edge units of a given class are present per hectare on the landscape? Generally, classes with higher proportions of the landscape will have larger edge densities, but it will not be exactly proportional, sort of like what we're seeing here between the two metrics. Next up, we're going to move on to a shape metric. So the one that we're going to look at is called perimeter area ratio. We can go ahead and run the functions both for Linero National Park and for Dane County landscapes, the landscape level rasters right now, which these lines of code will do. And this metric can show how shape complexity works. As perimeter to area ratio increases, the shape complexity also increases. Here is a very rough visual example of how perimeter to area ratio works. So both patches have the same area. The first patch is quite aggregated, so you get a lot of area per unit of perimeter. And the second patch is stretched out and skinny, so you get a lot of perimeter for every unit of area. This makes it have a higher perimeter to area ratio. And if one class has a lot of patches that look like the square shape, then on average, the perimeter area ratio for that patch or for that class or landscape will be low. And if another class has a lot of long and skinny patches like the irregular shape, then on average, that class or landscape will have a high perimeter to area ratio. So now we can go back and look at the results for the two landscape level metrics. Across both landscapes, the perimeter to area ratio is relatively close. However, Linene has a slightly higher ratio than Dane County at 0.293. So the patch shape is on average more complex than Dane County's patches. We can also calculate the perimeter to area ratio on a class level to see which of the land cover classes has the most complex shape on average. We can go ahead and run the class level metric for Linero National Park now. That's this line. And in the output, we'll see that the most complex class is 80 or permanent water bodies, and the least complex is 20 or shrubland. So now we're going to move on to the next metric, and that is the Shannon Diversity Index, and it's a diversity metric. We can go ahead and run both of these lines of code to calculate this at the landscape level for each of our areas of interest. This is a very commonly used index in ecology, and it shows the number and relative evenness of different land cover classes. It takes into account the number of classes and abundance of each class. So the index starts at 0 and it has no upper limit, but it very rarely goes above 4. So that's sort of the range you're looking for. And it should be looked at relative to other landscapes or relative to 0. When the Shannon Diversity Index equals 0, when there is only a single patch present on the landscape, and it increases without limit as the number of classes increases while the proportions are equally distributed. For example, a landscape with 10 classes will have a higher index than a landscape with 1 class, and a landscape with 10 classes that are each 1/10 of the landscape, so evenly distributed, will have a higher index than the landscape with 10 classes where one of them takes up half of the total area. In our example here, Dane County has a Shannon Diversity Index of 1.34, which is higher than Linene's 1.16. We know that Dane County has less classes than Linero National Park from when we ran the check landscape function. So therefore, we know that Dane County's proportions are more evenly distributed than Linene's, but we can't determine the degree of that from this class alone, from this index alone. For an example of core area metric, we're going to look at core area index. Many species of conservation concern have minimum requirements for core area, which makes this an important metric when evaluating habitat for such species. This metric can be calculated on either a class or a landscape level, and there are a few extra settings that you can use to tailor this metric to what suits your data and analysis the best. We will use the class version of this metric and compare outputs when the edge depth is changed. So the core area index is the percentage of core area in relation to patch area. A cell is considered core area if the cell has no neighbor with a different value than itself. This can be measured in a 4 neighbor rule or an 8 neighbor rule. And like other functions, this is designated by the directions argument here. We'll go ahead and set it to 8 for the 8 neighbor rule, which is the default for most functions. And since we're calculating mean here, the index on average will be an average of the indices for every single patch within the class. So we can go ahead and run both inputs in case they take a little while. So you can run both of these. When we get the output, we'll see that the index can range from 0 to 100. 0 would indicate that 0% of the class is considered core area, where 100 would mean that all of the class is considered core area, which is not mathematically possible, but you can get very close. In our first example, I've used an edge depth of 1, which is the default. This means that any cell that's not directly adjacent to a cell of a different class would be considered core area. Using this edge density, all classes have index values that are over 1%. And the indices of the largest amount of core areas are tree cover, herbaceous wetlands, and grassland there. For the second input, we're going to adjust the edge depth to be 5. And I chose 5 because it applies to my own research. I conduct bird surveys on forest patches, and I only count birds when they're within 50 meters or more of the edge of the habitat. And if I were to use this data set and metric to find patches of forests that would work for my study, then I would want to set the edge depth to 5 since the raster is 10-meter resolution. When selecting and using landscape metrics, it is important to tailor them to your analysis, so that's why we're doing that here. When we run the function with an edge depth of 5, we see that only one of the classes has an index above 1, which is permanent water bodies, not a great place to survey forest birds. And this means that as a whole, the landscape is not looking fantastic for my bird surveys, though I would probably want to run this on a patch level if I was actually considering this as a study area. Our final landscape metric that we're going to look at today is contagion, which is an example of an aggregation metric. It's very commonly used landscape metric, and it's based on cell adjacencies. It describes the probability of two random cells belonging to the same class. And this shows how clumpy the landscape is, or more specifically, it measures how connected similar land cover types are across the area of interest. And it's based on how often different land cover types occur next to each other. Contagion values can range from 0 to 100. And when a value is near 0, it means that different land cover types are highly mixed and dispersed, and the landscape is generally fragmented. When a value is near 100, it's the opposite. We can go ahead and run these lines of code now. So here, while that's running, is a visualized example of a low contagion versus a high contagion landscape. In the low contagion landscape, the pixels of the same class are not clumped together, and you have a pretty good chance of finding pixels of different classes nearby each other. So it's clearly pretty highly fragmented, though not completely random. And in the high contagion example, you are very likely to find pixels of the same value near each other, and it is not fragmented, which we can see. Feel free to run the contagion functions for, oh, we already ran the contagion functions, but we're gonna see how they measured up. So Lenine National Park has a higher contagion value of near 70 here, meaning that the landscape is much clumpier and less fragmented than Dane County, which has a value of 57.7. Both of these are kind of in the middle. Neither one is looking too fragmented. So those were all the individual metrics that we're going to look over today, but there are still a couple of other more general functions that I wanted to go over. So first, we're going to use the calculate LSM function. Go ahead and start running this. I'm running either or both of these functions now because they might take a while to run, especially the first one. So do feel free to skip this one if you don't want to wait at this time. The second calculate LSM function is the more important one for the tutorial, but we'll look at this one first. So instead of calculating every landscape metric on its own, the package also has this function that allows you to calculate multiple metrics at a time. This function lets you filter for metrics of a specific type and level, which is what we're going to do in this first line of code. Or it allows you to set exactly which metrics you would like to calculate, which is on the next line of code and will be in the following slide. In this first line, we are calculating all available metrics at the landscape level here, and they are aggregation metrics, which is at a type. So let's see, sorry. And then we're going to also say that we want to use the 8 neighbor rule here using the directions argument. The output, when it does run, will show 14 metrics that all met those criteria and the values that it calculated for each of those metrics here. I won't go over what each of them mean now, but you can see that in row 3 is calculated the contagion metric, which is the one we just did in the last section. In the second example of using this function, we're going to tell the function to calculate all of the class level metrics that we used in the workshop so far using the what argument. So again, we'll list our raster here, which is Lenine, followed by what equals, and then our list of functions here. So we have core area index, and then mean area, and then the proportion of land cover and edge density. And again, we're going to tell it to use the 8 neighbor rule when it's necessary. So for this example, I'm going to set this function to create an object called metrics here using this arrow, um, instead of directly just printing the output, because we'll want to use it in the next function that I'll be showing. But when we do print the metrics object right here using this line, we'll see a table with all of the output metrics for every class. We already calculated these during the workshop, so I won't go over them again. But this is a quick way to approach calculating landscape metrics when you already know which metrics that you're interested in. All right. And this last function that I'm going to show you from the package is called the calculate correlation function. As I said in the beginning of this presentation, there are hundreds of landscape metrics available, and many of them are redundant. So one of the easiest things that you can do to narrow down your options is to create a correlation matrix and eliminate any of the metrics that are correlated with one another. We'll run this function using the object we just created in the last slide as the first argument, so that's metrics. And then we'll be using the Pearson correlation coefficient for our method. That's the default. And then we're going to set diagonal to be false. And that's just saying that we don't care if the metrics are correlated with themselves, because they always will be. We don't want to see that, so it'll be false. Based on the values of the output matrix, we can go ahead and eliminate any of the redundant metrics. You can decide what thresholds you want to set for your own research, but it's common to start getting rid of metrics when they have a correlation coefficient of about 0.7 or higher. So that's what we're going to do here. The only metrics that have a coefficient of 0.7 or higher are proportion of land and edge density. So these are both our area and edge metrics that we calculated in the beginning. And so you would go ahead then and decide which one you want to keep and which one you want to throw out, depending on which would be more helpful for your research or if one of them is more correlated with other metrics as well. And even with the correlation matrix helping to eliminate some of these options, there will still be many metrics to choose from, and not all of them are going to be relevant to your data or your questions. When researching potential metrics to use, it's important to keep your research questions in mind and consider what metrics or types of metrics can be used to best assess your landscape. Considering how many metrics there are, a lot of people have written papers trying to find the best ones. I've included 2 of these papers in the supplementary materials for this workshop, but it isn't a one-size-fits-all approach. I would recommend reading through the documentation for the metrics that you're interested in, and you can find those in the package documentation or the FragStats website, and they both do a really good job at explaining the math behind the methods and their intended use. Okay, so now we're just going to wrap up, and I wanted to say thank you again for coming to this workshop. The landscape metrics package has way more metrics available than what I went over today. It's like 140. And it also has a few more useful general functions that I didn't have time to go over and weren't as applicable to this workshop. If you didn't get the chance to download the supplementary material before the workshop, or if I moved too fast through the tutorial, please feel free to download it now or later and go through it when it's convenient for you. I have step-by-step instructions that are included in the code, and the supplementary material also has a few more resources on metrics as well as documentation for every data set or package that I mentioned today. And now we just have time for a couple of questions.
Para un par de preguntas, si quieren hacerlas en el chat, por favor. Bueno, como mencionó Paige, muchas gracias a todos por asistir al taller y ahora estamos pendientes de cualquier pregunta que tengan, la pueden escribir en el chat, por favor. So first question is, where can we find the complementary material?
I believe it was emailed out to people beforehand, but if you did not get that email, I guess let us know and we can get it to people.
Ok, Noelia, Nati mandó el material por email, creo que ayer, pero por favor avísennos si no les llegó el correo por el chat y podemos revisar qué pasó. Ujú. Tranquila. Ok. Quedamos pendientes de cualquier otra pregunta que tengan. También si les queda más fácil pueden alzar la manito y preguntar con el audio. Paige, next question is if the edge is always calculated with the number of pixels based on the resolution.
It is it is often calculated as pixel number. There are some metrics that use distance, like which is why it's required to be in meters as their unit of measurement. But most of the time, if you're looking at like edge density, then it's just number of pixels.
Ujú. En la mayoría de veces sí se usa el número de píxeles. Hay algunas métricas que usan distancia en metros y por eso es importante que nuestro raster esté proyectado en un sistema de coordenadas que esté en metros. Pero para la mayoría de veces y sobre todo para la densidad del borde sí se usa el número de píxeles. Mhm. And next question is in English. So, is the diversity index influenced by factors like area, edge, or other factors? And I'm going to translate to Spanish. Entonces, la siguiente pregunta de César es si este índice de diversidad se ve influenciado por factores como el área, borde u otros factores.
Right. So it's calculated by patch area of
Oh,
different classes. So it's a metric that is reported on the landscape level, but is calculated by patch of class type, patch area of classes.
ok. La respuesta a esa pregunta de César es que para este índice se usa digamos, se calcula el área de los parches de cada clase. Entonces, digamos que ese es el único factor que se tiene en cuenta en el índice. Eh, Next question is, do you always need to work with a raster? There is no possibility to use it with shapefiles.
Yes, in landscape metrics package, you have to use a raster. I have seen some papers that talk about using shape files, but I think in like if you're allowed to use shape files, but I think in most cases you would want to rasterize shape files to use it. But that's something that you can do in GIS softwares or in R too,
Ujú.
using the Terra package. There's a rasterize function.
Ok, para la pregunta de Nikki, si se debe trabajar siempre con raster, la respuesta es que el paquete de Landscape Metrics sí usa, digamos, este tipo de archivo para trabajar. Hay algunos papers que evalúan la posibilidad de usarlo con shapefile, pero en este momento digamos que sí se usa únicamente con rasters. Entonces la recomendación es que si tienen un polígono lo puedan rasterizar y esto se puede hacer en un software de SIG o también se puede hacer directamente en R. Por ejemplo, el paquete de Terra tiene una función que se llama rasterize y que puede convertir los shapefiles en rasters. Eh, Next question is there a rule to see the correlated variables? You talked about when two variables are correlated, you use 0.7 as your limit to not use one of them.
Mhm. Yeah, generally, I think people make the cutoff at about zero point 0.7 or 0.65 to be correlated, but there are people can make an argument for it to be from zero point 0.6 to zero point 0.9. Like I've seen all of that depending on who's doing the research and what your goal is. So it's sort of a personal choice and based on the literature in your field.
Okay. Para la pregunta de Lucía, dice que Paige dice que ha visto que hay personas que usualmente usan ese límite de 0.65 a 0.7. Sin embargo, hay como varios artículos que pueden usar un límite diferente, por ejemplo, de 0,5 a 0,9, y eso depende mucho, digamos, de la investigación, es como una decisión personal y también basada en la literatura, digamos, del campo de estudio específico del proyecto. Ujú. Que thanks, people say thanks. Am, ¿Listo? ¿Alguna otra pregunta? Bueno, I think people. Oh, con mucho gusto, Nati. Thank you, Paige, for the presentation. A lot of people say that thank you and that it was very interesting. And I think we don't have more questions. So, ujú. Muchas gracias a todos de nuevo por unirse a este taller y esperamos verlos dentro de 8 días. Y ya, muchas gracias a todos. Espero que tengan un buen día. Entonces,
Thank
bye
you.
everyone.
Bye.
Chao a todos. Gracias.
Very nice, Paige.
Yeah, thank you.
Yeah.
See y'all later.
Yeah. Okay. Bye-bye.